Welcome back. In the previous video, we introduced the concept of Agentic AI and explored how it differs from traditional AI by going beyond simple conversation to planning, reasoning, and taking action autonomously. So, before we move forward, let's do a quick recap using a few new real world examples. Sometimes seeing the same concept from different perspectives makes it much easier to understand. We will revisit the core ideas with practical scenarios and compare agentic AI with conventional AI system so the difference becomes crystal clear. Imagine this is for a moment. Suppose you own a company and tomorrow someone gives you 5 incredibly smart employees. The interesting part, they never sleep. They don't get tired. They don't complain. They don't wait for instructions every 5 minutes. You simply tell them, I need this project finished. And they figure out the entire process themselves. They research, they make decisions, they use the right tools, they solve problems. Finally, they come back with completed work. Sounds impossible? Just a few years ago, it was. Today, this is exactly the direction artificial intelligence is moving. This new generation of AI is called Agentic AI. Unlike traditional chatbots that simply answer questions, AI agents can actually perform tasks and make decisions, use software, and work towards completing a goal. So, in this video, we are going to understand Agentic AI from absolute zero. We will first understand what artificial intelligence actually is. Then we will see how large language model work. After that, we will learn how AI agents think, how they remember information, how they use tools. With RAG is why data or database vector or vector database exist, what MCP does, and finally how companies are building powerful AI system using multiple AI agents working together. So don't worry if these terms sound confusing. By the end of this video, every single one of them will make sense. So let's begin from the very beginning. So before understanding agentic AI, we first need to understand artificial intelligence itself, because agentic AI is simply the next step in AI's revolution. Let's start with something everyone already knows. Imagine I ask you to build a calculator. A traditional programmer will write every instruction manually. If the user presses plus button, it will perform addition. If they press minus button, then it will perform subtraction. If they divide something by 0, show an error. So every possible situation has to be programmed by a human. This approach is called a traditional programming. The computer doesn't think, it simply follows instructions. Think of it like following a cooking recipe. If the recipe says add 2 spoons of sugar, you add exactly 2 spoons, nothing more than, nothing less. Now imagine a completely different problem. Suppose you want a computer to recognize whether an image contains a cat or a dog. So can you write rules for every possible dog? Not possible. What about a white dog, a black dog, a puppy, a dog sleeping, a dog partially hidden? Very quickly you will realize that writing rules for every possibility is almost impossible. So instead of writing rules, we change the approach. We show the computer thousands or even millions of pictures. Some are labeled. Labeled means labeled with dog. Some are labeled with cat. Slowly the computer starts discovering patterns by itself. It notices something human never explicitly told it. Ear shapes, body structure, face proportion, textures. Over time, it becomes surprisingly good at identifying animals it has never seen before. That's the basic idea behind artificial intelligence. Instead of humans creating the rules, the machine learns the rules from examples. This is very similar to how children learn. When a child learns what a dog is, nobody gives them a scientific definition. Parents simply point and say, "That's a dog." After seeing enough dogs, the child naturally recognizes new ones. AI learns in almost the same way. The only difference is that instead of using biological neurons like our brain, it uses mathematical model called neural networks. So artificial intelligence didn't become powerful overnight. It evolved over several decades. Let's look the three major stages. The earliest AI systems were basically giant collection of rules. Experts mainly manually wrote thousands of if-then statements. For example, if a patient has a fever and cough, then suggest influenza. These systems worked well until they encountered situation nobody had predicted. The moment reality changed, the systems failed. So they had almost no flexibility. Stage 2, researchers then asked an important question: what if computers could learn patterns directly from data? This idea led to a machine learning. Instead of writing rules, we trained models using examples. Algorithms such as decision trees, support vector machine, and early neural networks became popular. They performed much better than rule based systems. But there was still a problem. Each model could perform only one job. One model recognized handwritten digits, another predicted house prices, another can detect spam emails. Every problem required a completely different model. AI was becoming smarter, but it was still highly specialized. Everything changed in 2017. Researchers at Google published a paper called "Attention is All You Need." That paper introduced a completely new architecture called the transformer. Almost every modern AI system today, including ChatGPT, Claude, Gemini, and many others, is built using the fundamental idea. So, why it was such a breakthrough? Let's use a simple example. Imagine you are reading this sentence: the fisherman sat near the bank and watched the river flow. When you read the word bank, your brain immediately understands that is it refers to the side of a river, not a financial bank. How? Because your brain considers the entire sentence. Earlier, AI systems struggled with this kind of understanding because they processed text mostly one word at a time. Transformer introduced something called attention. Instead of focusing on just the next word, they examine relationship between all the important words in a sentence simultaneously. That allows the model to understand context much more effectively. This single innovation completely transformed modern AI. And once researchers realized that, larger transformer trained on more data become dramatically more capable. The era of large language model (LLMs). Now the question arises: how large language model actually works? As we have understood how modern AI evolved, let's talk about the technology that made tools like ChatGPT, Claude, Gemini, and many others possible. These systems are powered by something called large language models or LLMs. You hear this term everywhere these days, but what exactly is an LLM? Is it thinking like a human? Does it understand language the way we do? Or is something else happening behind the scene? Let's break down step by step. A large language model is essentially a computer program that has been trained on enormous amount of text. During training, it reads books, articles, websites, research papers, documentation, conversations, and many other publicly available sources of information. Its goal isn't to memorize every sentence, instead, it learns pattern in language. It learns how words are related, which word usually appears together, how sentences are structured, how ideas flow from one sentence to next, even different writing styles, tones and formats. Think of it as someone who has spent years reading millions of books. They may not remember every page, word for word, but they develop an intuition how about language works. An LLM develops something similar, not consciousness or understanding in the human sense, but an incredibly sophisticated statistical understanding of language. Here is something that surprised the most people: the secret behind every LLM. Despite all the amazing things these AI systems can do, writing a code, explaining science, solving math problems, writing essays, creating business plans, the core task they are performing is actually much more simpler. At their heart, LLMs are prediction machines. More specifically, they predict the next token. That's it. Everything else emerges from doing this prediction extremely well. So, what is a token? You probably have heard people say the AI predicts the next word. That's close, but it's not completely accurate. LLMs actually work with tokens, not with words. A token is simply a small piece of text. Sometimes it's a whole word, sometimes it's only a part of a word, sometimes it's punctuation. For example, hello might be one token, helping might also be one token, but a longer word like extraordinary could be split into multiple tokens. Every Even a comma or a period can become its own token. Why do model use token instead of words? Because language are incredibly flexible. People create new words all the time. Technical terms constantly appears. So different language have different word structures. So by working with similar piece of text instead of complete words, the model becomes much more flexible and efficient. Now let's look at an example. Okay, imagine one type the following sentence into a ChatGPT. I am typing the capital of France is. The model now looks at everything that came before. It doesn't search Google, it doesn't browse Wikipedia. Instead, it calculates the probabilities. Internally, it asks something like, based on everything I have learned during training, which token is most likely to come next? Maybe the probability looks something like this. For example, coming Paris is 99.8%, coming of London is 0.1%, coming of Berlin is 0.05%, coming of Madrid is 0.03%. Since Paris has the highest probability, that's the token it generates. Now the sentence becomes the capital of France is Paris. The model repeats the exact same process again. Now it predicts the next token after Paris. Then the next, then the next. It keeps repeating the prediction process hundreds or even thousands of times every second until the response is completed. This means that every paragraph you read from an AI was created one token at a time, with each prediction depending on everything that came before it. Think of it like an extremely intelligent autocomplete. A useful analogy is the autocomplete feature on your smartphone. When you type good, Your keyboard may suggest morning, luck, night. It, it's predicting what you are most likely to type next. An LLM does same thing similar. But imagine an autocomplete system that has studied millions of books, programming, languages, scientific papers, websites, conversations, and technical manuals. Instead of predicting just one or two words, it can generate entire articles, write software, explain complex topics, solve reasoning problem, and even carry on long conversations. That's why many researchers describe modern LLM as autocomplete on an extraordinary scale. Of course, there are far more mathematics behind the scene, but this analogy gives you the right intuition. Now, why AI can sound serious one moment and creative the next? Now let's look about one of the most important settings you will encounter when working with language models. It's called temperature. The name sounds strange at first. We are not measuring actual heat. Instead, temperature controls how predictable or how creative the model's response become. Think about rolling a dice. If the dice is heavily weighted toward one number, you will always get the same result. If the weight is removed, many different outcomes become possible. Temperature works in a similar fashion. Imagine you are asking the AI, what is the boiling point of a water? There is only one clear factual answer. You don't want creativity here, you want accuracy. When the temperature is set very low, close to zero, the model almost always choose the most probable next token. The result is more consistent answer, more deterministic behavior, better factual response. This is ideal for programming, mathematics, documentation, data extraction, technical explanation. High temperature. Now imagine asking the AI, write a fantasy story about the dragons living on Mars. There isn't one correct answer. Creativity is valuable. With a higher temperature, the model becomes more willing to explore less probable word choices. The result is more imaginative writing, greater variety, unexpected ideas, more diverse responses. That's why higher temperatures are often used for story writing, brainstorming, marketing copy, creative content, fictions. A good way to think about it is this: low temperature is always equal to safe and precise. High temperature is always equal to creative and adventurous. Neither setting is better. The right choice depends entirely on the task. So next we will discuss about the AI's working memory, that is context window. The context window, this is one of the biggest limitation and also one of the biggest strength of modern language model. A simple way to think about it is as the AI's working memory. Imagine you are having a conversation with a friend. They remember everything you have discussed during the last 10 minutes. But if the conversation lasts for 8 hours, eventually they will start forgetting the details from the beginning. It happens in the real life. Language models behave in similar way. Everything inside the context window is visible to the model while it's generating its response. That includes your current question, previous messages, uploaded documents, tool outputs, instruction you have given earlier. The model can use all of this information while reasoning. However, anything that falls outside this window is no longer visible. From the model's perspective, it effectively disappears. So why does context size matters? Suppose you are asking an AI to analyze a 300-page legal contract document. If the entire document fits inside the context window, then the model can consider all of it simultaneously. It can connect ideas across distant sections. It can identify contradictions. It can also answer detailed questions accurately. But if the document is larger than the available context, part of it must be removed or retrieved later using a technique like RAG, which we will cover in the later chapters. This is why context window has become one of the biggest engineering consideration when building a AI systems. At first glance, it sounds obvious. A larger context window should always be better, but that's not entirely true. A larger context window also means more computation you will require, higher cost, longer response times, increased memory requirements. So in some situation, extremely large context can even make it harder for the model to focus on the most important information. Think of it like studying for an exam. If your desk contains only the textbook you are currently reading, your attention stays focused. But if your desk is covered with 50 books, hundreds of papers, notebooks, and sticky notes, finding the most relevant information becomes much more difficult. So language model faces a similar challenge. So when AI engineers choose a model, they don't simply ask which model has the biggest context window. Instead, they ask how much context does this particular application actually need. Choosing the right context size is an emerging decision that balance capability, speed, and cost. And you will also see later in this course techniques like retrieval augmented generation RAG allows us to overcome many of these limitations without requiring enormous context windows. So now that you have understand how language models generate text and managing information, we are ready to take the next step. Instead of using a LLM simply as a chatbot, we are going to transform it into something much more powerful, an AI agent. So in the next video, we will first understand the components of an AI agent. See you in the next video. Thank you. Please make sure you like this video and subscribe to the channel for more content.